In the example, a plank of length L with mass m is placed and two person of mass m1 and m2 moving opposite to each other. Then we have to find the distance x moved by the plank. Here xcmi initial will be equals to m1 x1 plus m into x1 plus l by 2 plus m2 into x plus l divided by m1 plus m2 plus m2, and xcm final will be m1 x1 plus l1 minus x plus m into x1 plus l by 2 minus x plus m2 into x1 plus l minus of l2 minus x divided by m1 plus m2 plus m. Now xcm initial equals to xcm final, hence x equals to m1 l1 minus m2 l2 by m1 plus m2 plus m. If l1 equals to l2 equals to l by 2, then x equal to m1 minus m2 into l by 2 by m1 plus m2 plus m. A block of mass m starts sliding on a wedge of mass m. This is the wedge. Find the distance covered by the wedge during the time the block reaches its bottom, as shown in the figure. Consider block moves in this direction, the distance x when the wedge moves in the left direction, a distance x when block comes to the bottom, because no net force is acting on the system. So xcm initial should be xcm final. Since sigma fx is equal to 0, this implies xcmi equals to xcmf, or m1 x1 plus m by x2 by m plus m equals to m x1 plus h cot alpha minus x plus m into x1 minus x2 minus x by m plus m. Following this, we get the desired result. From figure shown, find the distance moved by the ring on the horizontal rod. A ring is connected with the string with a block. At the instant the thread makes an angle alpha with the horizontal after the release of block of mass cap m. Here initial xcmi equals to m. If this distance is x1, then initial xcmi equals to m x1 plus m into x1 plus l divided by m plus n, and final xcm equals to m into x1 plus x plus m into x1 plus l cot alpha plus x divided by m plus n. Solving this, we will get the desired result. A bob of mass m is hanging by a thread of length L from the ceiling of a railroad car of mass cap m and can move on the horizontal plane without friction. The thread initially makes an angle alpha with the vertical. Find the distance moved by the car during the time thread makes an angle beta during the time beta less than alpha. Since sigma fx equal to 0, so xcmi equals to xcmf, or this implies m1 x1 plus m into x1 plus l dash by m plus m equals to m into under bracket x1 plus l dash under bracket sin alpha minus sin beta minus of x bracket close plus m into under bracket x1 plus l dash minus x bracket closed divided by m plus n. A cylinder of mass m and radius r is released from point A as shown in the figure. Find the distance moved by the wedge during the time the cylinder comes to the lowest position. Problem can be solved in the same method. From figure shown, find the number of bricks can be arranged without toppling. Here xcm equal to x1 plus l for not toppling. So this implies m into x1 plus l by 6 plus l by 2 m plus m into under bracket x1 plus 2l by 6 plus l by 2 plus dash plus m into x1 plus n minus 1 into l by 6 plus l by 2 that equals to x1 plus l. From the figure, if the system is released from rest, find acceleration of the center of mass. We have SCM equal to m1 a vector minus m2a divided by m1 plus m2, because a equals to m2 minus m1 into g by m1 plus m2. So m1 minus m2 by m1 plus m2 to the whole square into g. In the system is released from rest, find acceleration of system of center of mass. Here SCM equals to m1 a vector plus m2 a vector by m1 plus m2, or m into 2a cos alpha I cap plus 2a sin alpha j cap plus 4m vector 4m into under bracket minus a into j divided by 5m because m plus 4m. Now again 4mg minus 2t equals to 4m into a and t minus mg sin alpha m into 2a. Solving this problem we can get the desired result. A cell of mass m is initially at the position 0, 0, 0, 0, 2a and it suddenly explodes into two fragments having mass ratio 1:3. The small mass falls at the position a, 0 in the xy plane. Find the position of larger mass. Here sigma fx equal to 0, so xcmi equals to xcmf. This implies 0 equals to m into a plus m into x dash by 4m. Or sigma fy equal to 0 xcm y equal to ycmf. So 0 equals to m into a into 3m into y dash by 4m. From figure shown, find the maximum elongation of the spring. The acceleration of Cm is given by Acm equal to A equals to Af by m1 plus m2. If we consider center of mass as the frame of reference, then it will be the accelerated frame, and hence we have to apply pseudo force technique for analyzing the situation. Now external net force on m, F1 equal to F minus m1 into A, or F minus m1 into F by m1 plus m2, or m2 F by m1 plus m2. Similarly, net external force on m2, F2 equal to m2 into A in this direction, or m2 F by m1 plus m2. Let x1 is the elongation due to F1 and x2 the elongation due to F2. At this instant, when a spring has the elongation, meaning maximum elongation, now from work energy theorem, F1 x1 plus F2 x2 equal to 1 by 2k into x1 plus x2 to the whole square. Since at the maximum elongation the block comes to the rest momentarily. Solve the above problem in the earth frame of reference, find the maximum elongation. Now moment of inertia. It is also known as the second moment of mass and it is defined as the moment of inertia. It is also known as the second moment of mass and is defined as the moment of mass. It is property of any rigid body by virtue of which it has tendency to maintain its inertia of rest or motion. Mathematically it is defined as I equals to mr square for system per particle I y dash xx dash equals to m1 r1 square m2 r2 square plus mn rn square by mn rn square or sigma I equals to n mi ri square. I represent ith particle or ix dash. This is a moment of inertia about this axis. Ixx dash sigma I equal to n mi ri square. For a continuous distribution of mass, the moment of inertia is defined as Ixx integration y square dm or Iyy equal to integration x square dm. That is moment of inertia about xx dash axis will be y square dm and moment of inertia about y that is axis will be integration x square dm. The moment of inertia of any body depends upon the mass of the body, the radius of the body and above all the distribution of mass of the body. The moment of inertia of any two bodies contended or subtracted only when the axis of rotation remains same. Theorem on moment of inertia, parallel axis theorem. From parallel axis theorem we can find the moment of inertia of any rigid body about an axis parallel to the axis passing through the center of gravity of the body and can be given as Ixx dash equals to Icm plus m into r square. Icg plus m into r square. For example, in this case, Ixx dash equal to Icg plus m into L by 2 का whole square or ml square by 12 plus ml square by 4 equals to ml square by 3. Again here parallel axis theorem, from parallel axis theorem, this is a disk and this is the CG axis which passes through the center of gravity from the disk, and this is a parallel axis y dash. Then Ixx dash Icg plus m into r square and Icg equal to 1 by 2 m into r square plus mr square equal to 3 by 2 mr square. Perpendicular axis theorem. If body lie in xy plane and its moment of inertia about x axis and y axis are known and are given as Ix and Iy respectively, then moment of inertia about z axis, that is axis perpendicular to the plane containing the body, is given by the parallel axis theorem and state that Iz equal to Ix plus Iy. That is moment of inertia about z axis equal to moment of inertia about x axis plus moment of inertia about y axis. Here it is clear that moment of inertia Ix and Iy, that is moment of inertia is in the, that is moment of inertia about x and y axis is in the same plane, but z axis is perpendicular to xy plane. again if have the moment of inertia in the xz plane, then Iy, the moment of inertia along Iy will be Ix plus Iz. Similarly, Iz equal to Ix plus Iy can be calculated. Calculate moment of inertia. यहाँ Id plus Id equals to Icg or 2Id equal to mr square by 2, hence Id, that is moment of inertia about diameter is mr square by 4. Here moment of inertia Iz equals to Ix plus Iy equals to m by 12 L square plus b square. Again here Id plus Id equals to I, hence Id equals to I by 2. In this case I1 plus I2 equals to I3 plus I4. Ix is equal to Icg plus m into r square by m into r by 4 to the L square equals to mr square by plus m into r by 4 whole square. So Vc equal to omega into r by 2. Calculation of moment of inertia for a rod about one end, that is Ixx dash Ixy dash equal to integration of x square dm or 0 to L x square m by L dx or ml square by 3 about g Ixx dash integration x square dm integration minus L by 2 to plus L by 2 x square m by L into ds, hence Ixx dash equal to ml square by 12. Integration x square dm integration x square lambda naught plus kx dx. Here in this case under Ixx dash equals to integration x square dm minus L by 2 to L by 2 x square lambda naught plus k into L by 2 plus x into dx. In this case mg minus L, mg minus n equal to m into ACM, or sigma tau A equals to I into alpha, or mg into L by 2 cos theta equals to m L square by 3 into alpha. When theta is very small, mg into L by 2 equals to m L cube by 3 into alpha, or ACM equal to alpha into L by 2. So n equal to mg by 4. Example, ICM equals to minus L by 2 to L by 2 x sin theta whole square, because this is theta, so this length will be x sin theta, and by L into dx. For ring dig equal to r square dm equals to r square into m by 2 pi r into dl. So Ig equals integration dig 0 to 2 pi r square into m by 2 pi r into dl, or Icg equals to mr square. From the figure shown, find the moment of semicircular ring ring about the axis passing through O. Di integration r square dm or integration r square m by pi r into dl. So I equals to integration I di. Integration di equal to r square into m by pi r into 0 to pi r dl or equals to I m r square. Here from the parallel axis theorem, IC equals to ICG plus m into 2r bata pi whole square. So mr square equal to ICG plus m into 2r by pi का whole square, इसलिए ICG equals to mr square minus m into 2r pi का whole square. Again from parallel axis theorem, O equals to ICG plus m into r minus 2r pi का whole square, mr square minus m into 2r pi का whole square plus m into r minus 2r by pi का whole square. Find the moment of inertia of ring about an axis passing through point O. IC equal to ICG plus m into 2r bata pi to the whole square. mr square equal to ICG plus m into 2r by pi का whole square. Hence ICG equal to mr square minus m into 2r by pi का whole square. Again from parallel axis theorem, I0 equals to ICG plus m into under root r square plus 2r by pi का whole square to the whole square equals to mr square minus m into 2r by pi to the whole square plus mr square plus m into 2r by pi का whole square or equals to 2mr square. In this case, disk I is integration di integration dm into x square or 0 to r m by pi r square into 2 pi x dx into x square equals to mr square by 2. In this case, ICG integration di integration dm into r square m by pi r square 0 to r r cube dr 0 to 2 pi d theta equals to mr square by 2. Dm equal to m by pi r square into r d theta dr. This implies dm equals to m by pi by 2 r square into r d theta into dr, and ICG equal to integration di integration dm into r square or hence equals to m by pi r square by 2 0 to r r cube dr 0 to pi d theta plus minus mr square by 2. Second, integration of I dm into r square 0 to r m by pi r square by 2 into pi r dr into r square or equals to mr square by 2. In this case, I is going to integration dm into x square 0 to r m by pi r square by 4 under bracket pi r by 2 into dr into r square और mr square by 2 m by pi r square by 4 into r d theta into dr. Hence integration I di integration dm into r square m by pi r square by 4 0 to r 0 to r r cube dr and 0 to pi by 2 d theta mr square by 2. I x equal to ICG plus mr square by 1 by 2 mr square plus mr square 3 by 2 mr square.